just sending it. Okay, go
I
ahead,
have
sir.
yesterday's lecture. Okay, good evening, everyone. And I'm very happy to see everyone is here. I do not see the chat. So, Andy, you have to interrupt for questions. I don't mind interrupts. So the way I teach my lectures, that in the beginning, I summarize the lecture I taught before. And we essentially then start after the summary, a brief summary of maybe 10 slides, we start with the main lecture. So last time we talked about the electrical properties and how electrical methods are used in exploration. We are focusing mostly on green energy, but I also wanted to start out with the linkage to hydrocarbons. So for hydrocarbon exploration, we are looking for high value targets like subsalt targets, mapping salt dome, or mapping oil reservoirs away from the wellbore, structure one, or here when we are producing, we are sucking out the water coning. We want to see how much oil is still in the rim, and land as well as marine in hydrocarbon. We also talked about what type of models we have. Geophysicists always use models, and the most simple model is an isotropic model, and that is a really bad model. It's a very unrealistic model, and it's a very bad model. So the isotropic model is a model where the physical parameter is the same with depths in all directions, and the Earth doesn't work that way. Why? It's because of the weight of the Earth. And the weight of the Earth means that in the sand, there's less porosity as larger depths. And so the velocities or resistivities are higher at larger depths. And so we have an isotropic inhomogeneous Earth. But at every depth level in an isotropic version, the parameters are still the same. This is also unrealistic. The most realistic one is an anisotropic inhomogeneous model on the bottom right. How do we get there? We have shales, and shales built from organic matter that's deposited when the sea retracts from the land, and the rivers deposit the organic material, and they build the shales. And here we have an anisotropic homogeneous where the parameters are the same, and we add gravity or the weight to it, compaction, and we get an anisotropic inhomogeneous. So this is the realistic model. So if you want to do modeling, everything should be anisotropic inhomogeneous models. Anisotropy is the most difficult part to comprehend. And here we have anisotropy on the reservoir scale on the right. This is an image log, a resistivity image log. The white lines are the sands, the dark ones are the shales. And you can see that the Earth is layered at a reservoir scale. The reservoir scale is about 25 meters. At logging tool scale of about 3 meters, we still see the anisotropy. When you just pick any section out of this, we go to 2 feet, which is the highest resolution of logging tools, and we still have anisotropy. So we won't be able to resolve the anisotropy. Even at scanning electron microscope scale, which is 2.5 millimeters, we see anisotropy. So anisotropy we have at every scale. So anisotropy is a big problem. We need to capture anisotropy in our models. Otherwise, we make an error between 20 to 50%. How do we get to our models? We start out with a piece of rock and a scanning electron microscope picture, which is done at electron level. Then we go to a larger bulk volume. And here we see the grains and the pore space. In this pore space in red, we have oil. In black, we have water. Grains are generally water wet. So we always have some sort of water saturation in our reservoir fluids. And the most simple way to represent this is to make a sphere model where we have balls stacked on top of each other. We can calculate the sphere by taking a quarter, of course, 4 times is this volume, so it's all symmetric. And we have essentially the volume of a sphere minus the pore space, the volume of the cube minus the sphere volume, and that is the pore space divided by the cube itself. So what we are left is then the volume fraction of the pore space, and so the maximum porosity we can get in this sphere packing, which is the most optimized packing, is 48%. So if we ever see a porosity log with porosities higher than 48%, we have additional fractures to the normal matrix porosity that are adding to the porosity. Now, a rock of unit volume 1 consists out of the matrix, and the matrix are these grains, and the pore space we just calculated, and the pore space is a fraction. This is called the porosity. It's a dimensional parameters, and it's a volume of the pores divided by the total volume. So here you have the total volume is the cube, and here we have then the cube minus the porosity, and here we define it again. We also talked about Archie's law, and Archie's law is a way to look at the resistivity, and we say that a clean porous rock has no clay or other conductors, just the pore fluid, and then the rock resistivity is directly proportional to the water resistivity. And the rock is essentially controlled by the conductivity of the fluid, and this is called conductor water. Water-saturated rock, the resistivity of the rock is directly proportional to the resistivity of the water. And of course, in every linear equation, there's a proportionality factor. This one is called F, and F is also known as formation factor, which is the bulk resistivity of the rock divided by the water itself. And that's called the resistivity magnification of the non-conductive matrix. And the reason why it's a non-conductive matrix, because the water resistivity is always lower than the matrix resistivity. And so the formation factor is always high. And then when we look at the formation factor, you can also say that this is inverse proportional to the porosity, and it's A and M, these are constants, cementation constants, and they need to be derived empirical. So you plot the porosity versus the formation factor, and then you derive these, I am so sorry, and then you derive essentially A from these diagrams from the slope, okay? We also talked about what induction logs are. Induction logs are based on coils that induce a current, and the induced currents in the earth have the same direction as the coils. Lenz's rule, right-hand rule, the current flows and the field lines go around it, and so you get identical induction currents, and you get a horizontal resistivity and a vertical resistivity, but you mostly see the effect of the shales, which are these layers here, and they are low resistivity. And so how do you get the high resistivities of the sands? You essentially add coils in perpendicular direction, horizontal coils, and then you see the higher resistivity, the vertical resistivity of the sands. Here's an example of two complex reservoir analysis, where you calculate the oil saturation from the resistivity logs on the left with vertical and horizontal resistivity, vertical here, horizontal there. And here is the vertical in blue and the horizontal in red. It's exactly the opposite color. And the right one is from Schlumberger, and you have here the oil saturation from the horizontal resistivity, and you get significantly more vertical resistivity from the vertical coils. And you essentially see here 42% more oil in this log, and this is also 45%. So the increased resistivity is significant. Then we talked about through casing resistivity. We have the borehole here, one side of the borehole, this is casing. The casing is 1 million times more conductive than the formation, the rock. And when we inject a current in the casing, the current leaks into the formation, but it's 1 million times smaller. So how do we measure the current that leaks in the formation? We measure the current that leaks in the formation according to Kirchhoff's law, which says that the sum of all currents impressed at one node is equal to 0. That means the sum of these two minus the sum going in the other direction should be equals to 0. So if we take this, measure this current and take the difference, we know exactly how much leaks into the formation. And that's how through casing resistivity log works. Here are examples. This is an old log, 20 years old, an old induction log. And then we have in red the Baker and in blue the Schlumberger through casing resistivity log. And they match very well. And they also match the old induction logs. Remember, the induction log was measured without the casing. We also looked at the voltage levels, and we found out that lateral logs are in the millivolt, induction tools are in the microvolt, through casing resistivity in the nanovolt, and deep reading tools in the picovolt. It makes it even more difficult to measure. So deep reading tools are tools that go 20 or 200 meters in the formation from one wellbore or go to the surface. A normal zone of investigation of a log is 3 meters, and the deep reading tools are about 200 meters. We also learned that EM is important for well intervention, geothermal, and special minerals, and the resistivity contrast gives rise to the various responses in various ways. So we need to understand what is what, and different logging tools evaluate the different parameters. The key element is to link the borehole to the surface in order to apply the technique for geothermal applications. Part 2, methods and methodologies. So today I talk about mostly 2 methods that are commonly used, magnetotellurics and controlled source electromagnetics. And I'm hoping that Professor Pembonan is going to introduce controlled source electromagnetics to Indonesia.
Sure.
Everybody heard that. He's going to have to buy dinner if he hasn't done anything in 3 years. So to start out with, we talk about magnetotellurics, and I explained what magnetotellurics is. Under the controlled source electromagnetic methods, we have 2 methods. We have time domain electromagnetic methods, which use a single signal generating event, and we have frequency domain electromagnetic methods, which use a continuous signal generation event. First, magnetotellurics. Where does the magnetotelluric signal comes from? We have the Earth here, and you all recognize right here where the arrow is, the pointer is, that's where you have Indonesia. And you can see the Earth is very small in the context of it. This is the magnetic field. And when we have a solar outburst, then the sunspot activities push particles against the magnetosphere. The magnetic field lines of the Earth are called magnetosphere. And let's investigate what is happening with these field lines. So first we have the Earth's magnetic field, then we have a solar outburst, the solar outburst pushes the Earth's magnetic field, it deforms, it connects the magnetic field lines in the back. And when they connect, we have a short, and an electrical current flows in the magnetic field lines. And this electrical current generates a magnetic field itself, and this magnetic field goes as plane waved into the Earth. And this is shown here. Does anybody know how strong these currents are that are flowing in the magnetic field lines? You can unmute your microphone and speak. Nobody? 1 amp, 10 amps, 1,000 amp, 10,000 amp, 100,000 amperes. Anybody, any idea? Professor Andriadi.
10,000.
Between 10,000 to 100,000. So they're very large. Now, these are low frequencies. For higher frequencies, we have lightning as source of the electromagnetic field, and the lightning is distributed around the equator, and and you can see here a lot of lightning. You can also see here for Indonesia, right here, you have a lot of lightning activities. So these are frequencies up to 20 kilohertz. I don't know if this link still exists. Let me try. Here we go. There are the different galleries. Anyway, we're not going to the website. So we have a plane wave reaching the Earth. The higher frequencies get filtered out at shallow depths, and at larger depths, you only have these lower frequencies left over. At the poles, you can sometimes see these lightnings, these magnetic field lines, when they reach into the Earth, and this is a picture of those. So we then have these fields coming in here. We have in the geothermal case a magma chamber, a low resistivity chamber, and from there heat goes into formations. When they're fluid filled, it heats up, and in the best case scenario, you have boiled eggs coming to the surface. In the worst case scenario, you have a volcanic eruption and magma coming to the surface. And I think all of you in Indonesia are used to the worst case scenario. Or has anybody seen boiled eggs coming to the surface? No? I can understand that. So what we do is we measure with an array over the structure, and the array consists out of magnetic field and electric field measurements. We take the ratio of the magnetic field measurements, we multiply it by 0.2 and the frequency, and we obtain resistivities in two directions, in y-x direction and in x-y direction. And by taking the ratio of the electric and the magnetic field, we are canceling knowing the or not knowing the location of the sources in the magnetosphere. We're now going to the controlled source methods. For frequency methods, we have a transmitter, and in the transmitter, we send a sinusoid wave, and we have a receiver. And when we send a signal, the primary field connects to the receiver, and we want to see the secondary field coming from below. And so this is the source waveform. The secondary field comes from below. These are induced eddy currents. And at the receiver, we see the primary and secondary field superimposed. So we measure one value, where here is the primary field as reference, and the secondary field is in red. So what we are measuring is the secondary field, the amplitude change, and the phase, which means the horizontal shift in sinusoid from the original field. So these two parameters give us an idea on what's happening in the subsurface. In the time domain case, we have a transmitter that switches a square wave through a dipole, and we have a number of receivers. These are Bohr receivers. There are pictures. So this is Andri's toy that he was operating, and this current the induction current goes downwards, and as it hits a layer boundary, it goes outwards with increasing time. And these are the receivers. At the receiver, we see a signal being switched, and then the induction signal in the subsurface dies down with time. We average these together and get a strong signal. By averaging, we improve the signal to noise ratio, and we get a strong signal. We see that in examples later on. In the marine electromagnetic case, and we can do these measurements onshore as well as offshore. In the marine electromagnetic case, we put the receivers on the ocean floor, and we have either a transmitter or we use the plane wave from the surface, from the magnetosphere, and we the sources generate a secondary response in the reservoir where we have a resistivity contrast, and this resistivity contrast generates a response which is recorded at the receivers. Now, let's talk about hydrocarbon signatures. And hydrocarbons are resistive. So is CO2. And so hydrocarbons are resistive. This is a log. And the typical resistivity of a hydrocarbon-bearing reservoir is significantly higher than the surrounding medium. So this is where the oil is. Seawater resistivity is 0.3 ohmmeters. And again, the black shows that the grains are water wet. And here the blue is water bearing. And when it's black, it is oil bearing, the rock. And that's the case in the resistive area. How do we do controlled source electromagnetics offshore? We have a transmitter and a number of receiver, and we plot the magnitude, which is the measurements we do versus offset. We can also plot the phase versus offset. I told you before, we measure two parameters, amplitude and phase. So these get plotted, and you see the boat goes across, and here is a hydrocarbon-bearing reservoir, and here is a clean area, no oil. So we take this and copy it over to this side, and see then, this is the reference area, and see that we get an anomaly from our measurements. This is the reference one, and this anomaly is known as direct hydrocarbon indicator. The methods offshore use a transmitter, and also, just like in magnetotellurics, magnetic and electric field receivers. You can do this in time domain too, like I described before. And you have the electric fields shown. This is the buildup of the signal like before. These are the electric fields you measure. And time domain, marine time domain works very well in shallow water, and it doesn't work as well as frequency domain in deep water. So how do we acquire the data? In magnetotellurics, we acquire a time series. That means that every time step, we record a voltage and phase. And we build the ratio of the fields to remove the unknown source. We then get an impedance, and the impedance is the impedance of the fields and results into an apparent resistivity. In time domain CSEM, we have a broadband time series, and we normalize it to a half space and convert it to apparent resistivity. In frequency domain EM, marine, we can plot magnitude and phase versus offset. And we also then can carry out induced polarization effects, where we look at charge-up effects or longer decay effects than we have before. And we get to that later. So here we are looking at an example. This is from Hawaii. We have apparent resistivity and phase plots. This is the apparent resistivity in the two directions, perpendicular to each other. This is the raw data. Then the data is usually acquired as array, and these arrays come in three different forms. We have the 3D array where we use bins, and each of these bins is one set of data. We have helicopter-assisted complex lines and mountainous area, and these are normal 2D arrays. What is the difference? In a 3D array, we have, in this case, 20 stations, and only one of the stations has magnetic field measurements. The other ones only measure the electric field. We are utilizing the fact that the magnetic field doesn't vary much laterally, but the electric field does. And then we copy the magnetic field. We obtain, then in this case, 20 individual soundings in one bin. Here we've set up electric and magnetic fields at each of the sites, and it's helicopter assisted. And these, we have all 5 components and set up them side by side and move them along. Let's talk about equipment. There are several manufacturers. EM Seismic Integrated, which is the company I work for, and Lema in Ukraine, which is one of our subsidiaries. Then EM only, which is mostly magnetotellurics, is Phoenix, Metronics, and Song. They all barely survived in the 90s. It was stable, but at the moment, it's not so stable again. And really, Phoenix is the strongest company. They don't have the best equipment, but they have the best marketing. And usually use multiple coils to cover the entire frequency band. Many of them have one coil that can do that, many have low frequency academic systems. All MT systems can do frequency domain CSEM, but they cannot do time domain CSEM. So for reservoir monitoring, I believe only the KMS system can do it. The other ones do not have the appropriate amplifiers. Usually, in addition, time domain measurements are done, and often loop source time domain is shallower than 800 meters. And if you want to go deeper than 1,000 meters, you need to use a grounded dipole. Frequency domain onshore is mostly academic. It's not much done commercially. Time domain, there are some commercial applications. From China, we see time frequency domain, EM, and we see from the US focus source EM. Both of them are boutique measurements. They are not necessarily routine measurements. We are trying to make focus source EM on a routine basis, but the benefits are not clear. Induced polarization is still mostly custom-made. Here is our equipment, which is the KMSA 20. These are the high frequency coils, the low frequency coils. We also have a coil that does both, and the cables and the electrodes and the Wi-Fi connection. Now, the cost of the hardware was significantly reduced, but it's still not enough. That means we need to reduce the cost of the hardware even more than what we've already done. So here is a Phoenix system. This is in Hungary. This is in Hungary. And here are calibration sites with the electrodes and the systems next to each other. We're talking about CSEM equipment. Now, for great depths, mostly geothermal, the only commercial system available is ours, and it was used in 2015 in Thailand, 2021 in the USA, and 2022 in Saudi, and I guess it's now being used in China as well next month. And in the 1990s, there was a seismic system modified, the TMAX or Summit, which was used in South Africa, France, China, Australia, Israel, India, Indonesia, and Italy. Some results are available, not all of the measurements. Of course, other manufacturers claim that they can do it too, Zong and Phoenix, but the results are clearly have issues with amplifiers. There are some Russian and Chinese-made systems, and of course, the Russians and the Chinese say they work very well. Here are some pictures from Thailand where the receiver loop is laid out. And apparently this must be a receiver. And here are the connections for the cables. You can see geophones and electrodes. How do we fit in the bigger picture in terms of frequency? We have 10 kilohertz, 1 hertz, and 10 to the minus 4. Geophysical measurements go all the way from 10 to the minus 4 to 10 kilohertz. Magnetocardiography covers a smaller range, and then you have industrial applications. Most industrial applications cover a range, like for cars and things like that. This is an old system, or older systems we made at University of Cologne. This was actually already a commercial system. And these are examples from China. This is a Chinese Mercedes truck. Now, where is it? And this is an Indian Jeep. And this is the system in the laboratory. The sensors, these are integrated. These are the electrodes. I am sorry that my fingers are so fidgety. These are magnetometers, flux gate magnetometers of various types, and these are coils, air coils. This is the 1, 2, 3, and these are other systems. This is a marine system, and this is a borehole receiver. This is a shallow borehole system. This is the TMAX system I talked about, built by a German seismic company, and the TMAX system. The TMAX system was built in 1991. We then also have well, we've seen this. So this is a system we saw before. This is our system with all of the different components explained again and all the receivers. So this system can also hook up with seismic 3-component geophones. And here is a 195 system configured to be used over a water flood, where this is the water flood, and these are the different receivers. The transmitter is somewhere off to the side. So you can modular configure the system to record electromagnetic and seismic system signals at the same time. As I said before, in 3D acquisition, you have at the center magnetic field and E-field measurements, and you copy the magnetic field to all the other sides. Before 1980, magnetotelluric was done single site with some remote reference. In the mid-1980s to the with 209, people would do line measurements, and the Phoenix system was developed in the 1980s in Denver. My roommate was working on the Phoenix system. I went to Australia and then worked on an Australian system. And I helped also EMI to build their system and Medtronics as well when I went to Germany. So I've been involved with many different system designs. After 2009, people started acquiring us in bins. For LOTEM, to 1990, multi-channel systems existed. In 2010, 3D arrays existed and joint inversion. And 2022, we have back nodes again and cloud connection to get more data. The cloud connection means that we have at the transmitter, the transmitter controller, and it sends the data to an FTP server in the cloud and also from the receivers. And you put a monkey at the receiver side, that monkey checks the data, uploads it, and gets feedback. If it's green, they move the receiver. If it's red, they leave the receiver there until the data quality is good. So what qualifies you to become such a monkey? Chayu. What is the qualification to become the monkey that does the quality assurance?
Has to be experience geophysics, know how the good data looks like and what
Yes.
does bad data looks like.
And must come from a geographic area where monkeys are commonplace.
Yeah, has experience in that area. Yeah.
You know, he must know monkeys. So, where are monkeys? Do you have monkeys in Indonesia? Yes or no?
Yeah, we do a lot.
And in India, they also have monkeys. In Thailand, they also have monkeys. In China, not many monkeys, except in southern China. So you cannot be Russian, you cannot be European, no monkeys. So this is, I'm saying this for the students. So there's a lot of jobs where you can do quality assurance on geophysical crews. So this is a different system. This is the 195 channel system with the seismic geophones and 100 kilowatt transmitter. This is the picture of the transmitter, and this is a 150 kilowatt transmitter. Now, the transmitter gets connected to a generator and then injects a current in the ground. And you measure and control the transmitter also. And then you have some certain safety equipment for this, and you can do some processing directly there. These are some transmitter sites from Germany in the 1980s, from China. Chayu actually took this picture. India. These are more transmitter sites. This is a borehole transmitter from Schlumberger. This is a 0.5 megawatt transmitter from Arizona, 1981, 200 kilowatt, 100 kilowatt, 100 kilowatt, 30 kilowatt, and these are 150 kilowatt. And this is very recent from 2022. This is wrong. Yeah, 21 to January 22. And this is in Saudi Arabia. And this is a 200 kilowatt generator, the diesel tank. And here the sensors are put into the ground. And both Andri as well as Chayu were working with this data. In the marine environment, how does the equipment look? We have EM receivers dropped at the ocean floor, and we tow the source about 30 meters above the ocean floor. So the receiver consists out of the transmitter consists out of a horizontal electric dipole, has a tail electrode, a streamer, and a lead electrode. And this is a typical electric field of such a dipole. And these are pictures of the lead electrode and the tail electrode. And this is a towfish. The towfish is essentially the beginning of the streamer, and the power goes as 3 phases down to it and gets converted in the towfish to DC, high voltage DC, and then up to 8,000 amps get injected into the ground. And this is a picture of the umbilical on the ship. And then you have a tail boil. What is the tail boil being used for, Andre?
But I don't have idea for it.
You don't what?
I don't have any idea. Because
The tail boil is for navigation, because the
for GPS.
toadfish, of course, you know where it is, but the tail boil moves around. So the tail boil tells you where the end of the electrode is. And these are more pictures. Nah. There's the end electrode. These are the receivers. The magnetic fields, the magnetic field sensor in this direction, there's a vertical magnetic field sensor. These are the electric field sensors. And the data logger is in there. These are the receivers on the ship being prepared to be thrown offshore. This is our test system in Greece to be thrown offshore, and there the system is being released. So what do? We receive a calibrated data as raw input to our data processing. And we receive voltages and parameters from the measurements, and we calculate apparent resistivities. We make sure our fields are correctly calibrated, and we then try to establish an image. Now, the output of our data processing are optimum improved calibrated responses and improved data calibration, and the data files are delivered as electrical data interchange format, EDI format from the SCG, as apparent resistivities, and of course, we provide backup files. Here is an example of a data set. We have the magnetic field HX and HY at the bottom, and these are electric fields, EX in pink, EY in red. These are 4 different electric field receivers on only one magnetic field receiver. And you can see that an activity in the magnetic field can be seen in all of these traces. We then take this time series, we convert it to frequency domain, and we do some processing and calculate the apparent resistivities. If we don't do much processing, the data gets noisy. One of the ratios is XY and one is YX perpendicular to it. But if you do some robust processing, you can clean up the data. Since the electromagnetic signal changes smoothly, you can clean up the data. It's really funny when this late at night, people are walking in my house and the people don't show up. It's actually the dogs going in and out. Scares me. So when you hear this dong dong, that's somebody walking in the house. And on the right side, after we process this data becomes smooth. This is the same data, but after processing. So then after we've processed the data, we are trying to interpret the data. Now, for CSEM data, this is different. These are different raw data sets. This is old processing, the noise in the data itself, and this is then the filtered data, and then the average data stacked data. And the data gets converted to resistivity transforms. These are 2 different resistivity transforms, which are also inverted on the right side. This is more modern data. And in the more modern data, we can see the raw time series on the left, and on the right side, we have the process time series averaged with the electric field. If you control your data acquisition correctly, you do not need to apply any filtering, and you get this type of response. what else do you do with the data? With new modern system, you run inversions, and these are 5 channels for one receiver, and you get an inversion result in red, and you compare it with some calibrated reference model, and the match between the inversion response in red and the data is as good as you can see here. So this is very good results. If this happens, automatically your data is good. But we still don't know everything about it. We still need to understand on the quality of the data. And when we do the inversion, and Andrea, have you already talked about inversion?
Not yet. This is
Now, I skipped that part in the logging. I looked at the log inversion results, but I didn't explain what inversion is.
yes, it is.
So you need to explain what inversion is.
Of course, there is a will be in the lectures. Sure, don't worry.
So in the inversion, you have because electromagnetic measurements cannot go negative, but when you do an optimization, an inversion is an optimization where you calculate many models and you compare them and you change the model until the model matches, the response from the model matches the data. So when you do this optimization, you do this with logarithmic parameters that can vary widely and randomly. But logarithms don't go really to zero. The physical parameters also not. And then when you go back, you transfer those inversion parameters back to the physical parameters. First, you transfer them to the logarithmic parameters, which are the inversion parameters, and then you transfer them back to the resistivities. And you want to know that your data has the sensitivity you're looking for. And so what you do is you establish a matrix between the inversion parameters and the physical parameters. And this matrix is multidimensional for all of the layers and gives you eigenvalues. And when you plot these eigenvalues, when they are distributed like white noise, that says that you have sensitivity all the way to the lowest layer. We have in this model 31 layers. That means we have 32 resistivities and 31 thicknesses. And you can see that the data is evenly distributed. Maybe here there's a little bit more weight to the near surface and here as well. But otherwise, this data set is sensitive all the way down to the 31 layers. I'm sorry about that, but Mali, be quiet. And so for all fields from the inversion, the data is very well fit, is what this says, because the eigenvalues are distributed like white noise. Here we have 1.5 kilometers, and we are trying to look 3 kilometers deep. And we have the inversion models plotted, and here are the reservoirs. This is from a CO2 injection pilot. And we can see that the inversion models match the reservoir quite nicely. Now, inversion is a preferred tool for geophysicists because it's model-based. In reality, inversion is a terrible tool because inversion puts too many ideas of the user into it. The user makes the model, and the minute a geophysicist makes the model, it's already wrong. So you really want to image the data. You want to transform the data, just like seismic data, that you can see what's in the subsurface. And many people have tried to do this. In magnetotellurics, there are some names here, and in time domain EM are some names. Today, this is not satisfactory. And I'll show you in the next example why. Here we have a section from South Africa. This is a very unique section, and this is known as a cut craton. This is a Kapval craton. And I only have known one other craton where EM measurements have been done in Malaysia. And what you are seeing here are two things. You see, number one, depths, and we are looking down to 40 kilometers here. Hang on a minute. I'm going to kick the dogs out the door. Dogs, you're going to go in the garden. Come on.
Oke, kalau ada yang mau bertanya silakan ya. Nanti bisa bahasa Indonesia, nanti saya bisa terjemahkan ya, enggak apa-apa ya. Kalau mau bahasa Inggris juga enggak apa-apa, silakan ya. Enggak usah
Andre,
malu-malu
you
ya.
must Deutsch sprechen.
Oke, go ahead, Scott.
So, so these are resistivity images displayed for these sites. Red are conductors, and blue are the resistors. On top of this, we have deep DC resistivity soundings using up to 200-kilometer long current electrode injections using power lines. This is from South Africa. And you note here that there is a good correlation between the deep resistivity with the conductive zones, and here the conductive zone, and here. But the inversion itself, because the inversion doesn't anticipate the complexity of the model, is garbage. It is uninterpretable. And I'm showing you in a second the inversion result. This is the inversion result. There is no resemblance between the geology and this result. So inversion is not always a very good tool. In particular, in complex environments. Next, I'm showing you an image from magnetotelluric measurements over a salt dome in Germany. And the outline of the salt dome comes from the gravity. These are the magnetotelluric lines. Station spacing is 50 and 100 meters. And the gravity and electromagnetic image the overhang of the salt dome and the salt dome itself. And this was drilled afterwards and gave fantastic results and additional drilling targets. So this was a very, very good case history. It's also published. I need to write this down, 67 reference. So, why is controlled source electromagnetic not more in common use? 3 nuggets. In the 1990s, we stopped using CSEM because we clearly knew we could not understand the anisotropy because we didn't have the vertical resistivity from boreholes. Now it's available. The 3D induction log exists. We can measure it and we know how to derive it. In the 1990s, we didn't know how to do it. All we would know is how big of an error we would do and that our measurements were not good enough. Now, the information focus, and we'll talk about this hopefully later, the information focus is still not clear, and we need new solutions. And these new solutions are either with focus source measurements or with borehole measurements. You've seen the borehole receiver, and I'm hoping that I have put in this, yes, I do. About 6 slides down, you will see the focus source EM measurements and how we improve it. And the other part is how to resolve resistive layers. And marine electromagnetics has shown us how to resolve resistive layers consistency. And today we have 3D inversion. So we have essentially addressed the 3 nuggets, and now it's up to us to apply CSEM and make it a more usable tool. We've talked about this yesterday, anisotropy and how important it is. So we do need to measure the electric field to see resistors in the CO2 case, as well as in the oil case. For geothermal, resistors are not so important, so electric fields are not so important for geothermal measurements. I emphasized already that anisotropy is everywhere, and we've seen this diagram. Now let's go about the focus. We have a sensitivity density for frequency domain and for time domain. And in time domain, we have the investigation zone near the transmitter and receiver. In the frequency domain, we're sampling the whole half space below the transmitter and the receiver. And so when we take the difference between 2 receivers, then we are left with the information between the receivers. And in the frequency domain, we see the currents coming up from the bottom. This is for 2 different frequencies. And for the time domain, we see the same thing for 2 different times. So the focus source EM, where we take the difference between these, allows us to see more information directly below the receiver. And here are 2 examples for modeling. These are 3D models. Time domain, you get differences between different times, and frequency domain, you get also difference between different times. And the anomaly is 40% for the big one and 10% for the little one. And then when we do a focus source EM, the anomaly is 200% for the big one and 40% for the little one. So smaller reservoirs can be detected, we get higher spatial resolution, and we can remove the shallow structure. Borehole measurements, when we are essentially putting a vertical electric field receiver in the borehole, can also significantly improve this. And here are essentially examples that we can do these borehole measurements with and without casing. And the signals are still very big there in the, this is about 100 microtesla. So they're in the microtesla range, and the resolution of the magnetic field sensor is picotesla. So a borehole tool would be installed in a borehole with a 3-component magnetic field receiver and electric field electrodes outside of the casing, X and Y at the surface, because you need to compensate for the deviation of the borehole. And this is a borehole tool in its transportation case. Now we've calculated the response for 3 sites at 10 meters depth, and we can clearly see for different distances between transmitter and receiver differences in the curves, and essentially we can resolve better the variations by going to the borehole tool, which is essentially the same result as with the focus source EM. Quickly about processing, MT processing and CSEM processing. We've already talked about the MT processing, so I skip this. Now, when we invert the data, we invert the data using 2-dimensional inversions. This is a salt dome inversion, and you can see the inversion result. This is a stable inversion from the data you saw before. Now, 3D inversion is essential. 3D inversion models are not always related to the 2D inversion models. They can be, but they're not always related. We have to often add constraints and rerun it. The most important part is integrating your results with geology. Now, these are CSEM layouts. This is the TMAX. This is the 2015 KMS system. We've seen this layout. You add transmitters to it, and then record for CSEM. Another important part is that you need to calibrate your system, you need to calibrate your sensors, you need to calibrate the receiver gains, you need to calibrate transmitter synchronization, and you need to make sure that you separate the instrument response from the Earth response and the coupling. Now, when you process the data, magnetotelluric processing includes frequency domain conversion, then robust processing, apparent resistivity, and time domain processing does a lot of pre-stack filtering, averaging, and then inversion. All of them include inversion. And then, this is LOTEM and TCSEM. And TCSEM is the marine version. So this is the marine time domain version because the system is identical. Now, today, this has been even more simplified and standardized. And so essentially, these can be very much automated and even with microseismic data. And then the inversion steps are on the right side. Some more data, these are noisy records. And these are pre-stack filters, these are post-stack filters. You can see pre-stack processing is better and gives you less noise. This is the noise envelope in the data. These are resistivity transforms. And when you image this data, you get colorful things. This is a layered inversion. This is an Occam image, which is smooth. This is an apparent resistivity image. And here you actually have a dike that you see in the data at the surface, which you can also see with 3D modeling. And we are almost at the end. So misunderstanding in parametric models is always a limitation. So the geophysicist is his or her own enemy. Anisotropy is mandatory to consider, and you need to have an inversion strategy. And whatever your inversion is, you must include your geologic input. And in most cases, people don't do it. People don't consider static effects, and they just run things mechanically, and they're wondering why electromagnetics doesn't work. To summarize, magnetotellurics and CSEM are mature methods. MT is fully commercial. CSEM is commercial in the beginning. The data is robust, reliable, and the methods are excellent for fluid imaging. And in the full field scenario, we are now adding sensors in the borehole that we didn't have before, new logging tools, as well as surface land and surface offshore equipment. And the future is in the full field integration. Any questions?